Ladies and gentlemen, it is my pleasure to introduce Mark Schulman. He's a member of the Central Florida Computer Society, an author, a speaker, a web designer, software designer, and technology enthusiast. He has designed software and web applications for businesses from small medical practices to Fortune 500 companies. Mark speaks on a wide variety of technological issues, and he is published author of 7 computer books. Including using Unix, understanding Unix, and using Lotus Notes, all published by Q, which is a division of Macmillan McGraw-Hill. Did the spacecraft have computers? What were their goals? How did we accomplish these goals and land on the moon? Mark will answer these questions and all other questions during his presentation on computers to the moon. I will now turn the presentation over to Mark.
Thanks very much, Jerry. Can you hear me okay?
I can hear you fine.
Okay, great. All right. Well, thanks. I'm really excited to be here. My name is Mark, and it was interesting to hear somebody mention the books. They can all be found in the bargain bins now for about 25 cents a piece or so. So this presentation combines my 2 big interests. I've always obviously been fascinated by computers, but I also grew up in Central Florida during the height of the space race. And so I have a big interest in that. And so this presentation combines my 2 big interests. So what we're going to talk about today is the development of computers in the early space program and the little known role of how they got us to the moon. So first thing I want to talk about, and many of you I'm sure already know this, is what the state of computing was in the 1960s. So when you talked about computers back then, this is typically what you were talking about. This is a NASA computer center in 1966. It's called the Real-Time Computing Center, and it's where they computed the trajectories for all the Apollo missions. And this is what we typically meant back then when we talked about computers. Now, how about personal computers back in the 1960s? Well, if you were talking about personal computers, you're probably talking about something like this. And if you don't know what that is, ask me later. So what I'm going to focus on is the original spacecraft that the United States used from the beginning of the space race up until landing on the moon. And that would be these spacecraft right here. So we had the one-man Mercury program, the goal of which was to get the United States into space. Then that was followed by the 2-man Gemini program, and finally the Apollo program, which got us to the moon. And that involved 2 different spacecraft, and we'll talk about each one of those. So first, let's talk about Mercury and how computers factored into Mercury. So the Mercury project actually started, we were already in a space race with the Russians, but we hadn't yet set the goal of getting to the moon. That came a little bit later. So the goal of Mercury was just to put an American into space. So the program ran from 1961 to 1963, and it was originally supposed to have 7 flights, but there were actually only 6. And the Mercury flights were launched aboard Redstone rockets and Atlas rockets. Now, the interesting thing, and we'll see this as we go through this, both the Redstone and the Atlas rockets were originally designed as intercontinental ballistic missiles. That is, they were designed to carry nuclear warheads. So NASA, when they needed a rocket, they turned to the Air Force and they repurposed 2 of the rockets that they were already using as ballistic rockets to carry people into space. So again, each Mercury flight carried 1 astronaut, 6 different people flew. So let's talk about the computer that was on board in the Mercury spacecraft. Well, there wasn't one. Mercury was a very simple spacecraft. Looked like this. and the astronauts used to joke that you didn't get in it, you put it on. Tiny little spacecraft. And it really didn't need a computer because it couldn't do much in terms of maneuvering. The rocket launched it into space, either a suborbital flight or an orbital flight, and it orbited, for orbital flights, it orbited the Earth some number of times, and then it fired some rockets to come back. It couldn't actually control its trajectory in any way, so there wasn't much need for a computer. Here's what the control panel of the Mercury spacecraft looks like. And this is a Mercury that's in the Smithsonian Institute today. And you can see lots of buttons and switches and dials, but nothing that looks anything like computer equipment. And sure enough, it had no computer. So as far as computers go, not much to say about Mercury. So let's move ahead to the Gemini program that came next. Now, by the time Gemini flew, we knew that we were in a race to get to the moon. So the Gemini program not only was the next logical step in the American space program, but it specifically was designed to further the goal of getting us to the moon. So the Gemini program ran between 1965 and 1966, about 18 months total. There were 10 manned flights altogether, and each one carried a crew of 2 different people. 16 different astronauts flew on Gemini. Now, if you multiply that out, 10 flights, 2 people each, that would seem to be 20 people. And obviously what happened was 4 people flew on 2 different flights. And that's why there were only 16 different astronauts on them. Gemini was launched on a Titan intercontinental ballistic missile. And there again, NASA needed a rocket, and they turned to the Air Force, took their Titan II missile and repurposed it for the space program. Okay, so the goals of Gemini again were, the goals of Gemini were to perfect the techniques to get to the moon. And there were 3 specific goals that they needed to accomplish during this program. The first one was we needed to learn if we could work outside the spacecraft. So Americans had never been outside of a spacecraft before. We'd had spacesuits on, and theoretically, if the cabin got depressurized, the spacesuits would protect us from the vacuum of space. We didn't actually know any of this. So we needed to learn, obviously, if we're going to go to the moon and explore, we need to be sure that people can actually work outside of the spacecraft. Second goal was long duration flights. Flights to the moon were going to take as long as 2 weeks. And the longest flight we'd had up until Project Gemini started was 34 hours. So we needed to learn that humans could actually survive in space for as long as it was going to take to get to the moon. And finally, we needed to be able to maneuver and navigate in space. We needed to be able to change our orbit, to go from one body to another, from the Earth to the moon and back. We needed spacecraft to be able to rendezvous and dock. And if you're not familiar with the word rendezvous in this context, when we talk about space, what we're talking about is 2 spacecraft managing to find each other and meet up in space. And when we talk about docking, we're talking about the 2 spacecraft actually connecting to each other. So this is what we needed to accomplish in Project Gemini. So extravehicular activities, we didn't really need a computer to be able to do that. That was just an engineering challenge. To build spacesuits and spacecraft where humans could get out of them and walk in space was just, we needed to be able to design fabrics that could withstand the vacuum of space, oxygen supplies, that sort of thing. No real computers involved in accomplishing that. And we accomplished that goal on Gemini 4 in June of 1965 when Ed White took the first American spacewalk. Long duration flights also didn't really need a computer. We just needed to design spacecraft systems that could last, that could keep people alive for up to 2 weeks. And we accomplished that on Gemini 7 in December of 1965, when Jim Lovell and Frank Borman spent just a few hours short of 14 days in space. And it was absolutely grueling for them. Frank Borman talked a number of times that he just about died of boredom because there just wasn't anything to do. And he said he and Jim Lovell had been training together for so long, they'd already swapped all the stories they had, so they really didn't have much to talk about. So long duration and working outside the spacecraft were just basic engineering challenges that needed to be solved, didn't require computers. However, maneuvering in space, there is a reason they call this rocket science. Maneuvering in space is highly mathematical. It has to be done sometimes. You have to do those mathematical computations very quickly and in real time. And maneuvering in space is completely non-intuitive. You don't just point the spacecraft at something and fire the rockets. All sorts of weird things happen when you maneuver in space in terms of, if you want to speed up, you actually do that by slowing down and dropping into a higher orbit. So completely non-intuitive. We definitely needed a computer to be able to do this. But you saw the computer we had before. It was that huge room of computers. How were we ever going to manage to accomplish this sort of goal with a computer? Well, in the Gemini program, IBM developed a computer, and they gave it the clever name of the Gemini Onboard Computer, also known as the OBC. It was built by the IBM Federal Systems Division, which is the division that does contracts for the government. So it was a true digital computer, and it was the first computer to ever fly in space. Its specifications were not anything we would be impressed by today. So we're used to computers that have clock speeds in the gigahertz. This one had clock speeds in the kilohertz. It was about 1 million times slower than a computer we have today. It had only 4K of memory, and all the software had to fit into that. And yet, in spite of the fact that it wasn't a very powerful computer, it weighed almost 60 pounds. One of the things I find kind of interesting is that the Gemini spacecraft had two different types of places you could store equipment. They had the pressurized compartment, which is where the people were, and they had the unpressurized areas, which is where they put equipment that was going to be exposed to the vacuum of space. And the computer actually lived in the unpressurized area. So it could actually be exposed to a vacuum and work just fine. So here's what the cockpit of the Gemini looked like. And it's obviously a little more complicated than the Mercury. And I don't know if you can really tell in this program, but in this slide, but there's actually 2 seats there because it holds 2 people. But if you look around, it looks like it's just more lights, switches, and dials. Where's the computer? Well, it's actually in several different pieces. And there are the components that make up the computer right there. And we're going to look at each one of those, and I'm going to tell you how this worked. And you're going to be amazed that they managed to make this usable. So on the center pedestal there, the middle thing looks like this. It's got a little rotator switch on it with 6 positions, and that allowed it to run each one of the 6 hardwired programs that the computer had in it. So if you wanted to run a program, what you would do is turn that dial to the program that you wanted to run, and then you push the start button. And of course, there's an on-off switch there, and a reset switch, and a malfunction switch. So if I want to run the rendezvous program, I'd turn that little selector switch up to RNDZ, that stands for rendezvous, and I'd push the start button, and it would run. Now, how about data? How do I get data in and out of the computer? Well, you're going to love this. This is the computer's only display. Looks like this. Now, there's actually a button missing there. This was the best picture I could find, but it is missing a button that's labeled readout. So the Gemini computer had 100 memory locations where you could either store parameters that got used by a program, or the computer could put calculation results in those memory locations. And the astronauts, they were numbered 0 through 99, and the astronauts had to know the number associated with each of those memory locations and what they contained. And of course, they had a reference that told them this. There was no capability of displaying letters, and it could only display one number at a time. So if the astronaut wanted to see what was in memory location number 87 on the little numeric keypad there, he would key in an 87, and then hit the readout button, and the computer in that 5-digit display that's labeled message would display the number that was stored in that memory location. Similarly, if the astronaut wanted to enter a value into one of the memory locations, he would type all 7 digits. So if you wanted to store, say, the number 10,000 in memory location 45, he would type 4510000 and then hit the enter button, and that would enter the value in that memory location. And that's how the computer and the crew passed data back and forth. Really cumbersome by today's standards, but that's what they had to do. So before they would execute a program, it was up to them to get together the data that they needed, that the program was going to need to operate, and they had to key it in one value at a time by pushing each value into the correct memory location. And God help you if you got the wrong value in the wrong memory location. So, but then, how did you actually manage to use this to rendezvous with another craft or to change your orbit? That's really the key. And that's where this piece of equipment came in. So once you were running a program, which might be to rendezvous with another spacecraft or to change your orbit in some place, some way, the computer couldn't actually fly the spacecraft. The astronauts had to do that, but the computer could tell them what they needed to do, could tell them how much they needed to go forward or backward, left, right, up, down, how they had to thrust their engines in order to accomplish what they wanted to accomplish. And maybe you can see that right in the lower center of this photo, there's a little pistol grip controller that both the astronauts could use, and that's how they maneuvered the spacecraft. And they could follow this indicator to do what they needed to do. And despite the fact that it seems very cumbersome to us, it was actually very effective. In December of 1965, 2 Gemini spacecraft that were launched separately into separate orbits managed to maneuver and find each other. And here's the picture of one of the spacecraft taken from the other spacecraft. And they spent almost a day flying within a couple dozen feet of each other. In 1966, the United States 5 times launched this spacecraft. It's an unmanned spacecraft called the Agena Target Vehicle. And they would then launch a Gemini spacecraft, and their mission was to find this target, rendezvous with it, and the nose of their spacecraft could fit in the collar that you see on the left-hand side of the spacecraft. And so the 2 spacecraft could actually connect to each other and fly together as one spacecraft. And they could use the engine on the Agena to change the orbit of the Gemini spacecraft. So while they were connected, they could use the Agena's engine to maneuver. And so this gave them the skills that they were going to need during the Apollo program. Okay, with that said, let's get to the meat, which is the Apollo program. So each Apollo carried 3 crew members into space. The program ran from 1968, the manned part of the program ran from 1968 to 1972. It had 11 flights in the Lunar program. Now, the Apollo spacecraft was actually used 4 more times for programs that had nothing to do with going to the moon. But for what we're concerned with here, there were 11 lunar flights. Each one carried a crew of 3 astronauts, a total of 29 different astronauts. And again, there were 4 astronauts that flew twice, and that's why we don't have 33 different astronauts. They were launched aboard Saturn rockets, and the photo you see there is the Saturn V. And what was interesting about the Saturn rockets were they were the first rockets that were designed for no other purpose than to carry people. The Saturn rockets were never designed to be weapons. In fact, they would have made horrible weapons because they took so long to get ready for a launch and took so many people to get them ready. So never used as a weapon. And the goal of the Apollo program from the very, very beginning was to land people on the moon. And they succeeded. And we're going to see how they did this. 6 different missions landed on the moon. Different person on each one of those missions landed on the moon. So a total of 12 different Americans walked on the moon. Pulling this off was going to require a serious computer. And even a computer like the one Gemini had was not going to do the trick. So let's talk a little bit about the mission so that you can get a little bit of the terminology down. Some of you may remember this. I grew up during the Apollo program. I remember all of this. But for those of you that are a little bit younger, this may be new. So here's what we flew to the moon. Each lunar mission was actually 2 separate spacecraft. It was the command and service module, which is what you see, the cylindrical spacecraft there. And I'll frequently refer to this as just the command module because command and service module is just too long to say. And we have the lunar module, which was the part that actually landed on the moon. And it was actually divided into 2 sections. And maybe you can tell that there's kind of 2 pieces that make up the lunar module. The whole thing landed on the moon, but only the top half blasted off and went back into lunar orbit. So what would happen? Let me give you the 20-second overview of how a lunar mission ran. So the 2 spacecraft would be launched together and would fly to the moon together, which took about 3 days. And together they would enter lunar orbit, hooked up just like you see them here. When they were ready, the LEM, and I'm sorry, I will use the term LEM, LM, to talk about the lunar module. The LEM would then, 2 people would transfer from the command module into the lunar module, and those 2 people in the lunar module would separate, and the lunar module would get out of its orbit, would deorbit, and land on the moon. Meanwhile, while they were on the moon, the 1 remaining astronaut would stay in the command module and monitor the command module. The 2 people in the LEM would stay on the moon anywhere from 1 to 3 days, and the length of time on the moon progressively increased as the program went on. When they were done, the top half of the lunar module would lift off, and it would have to rendezvous and dock with the command module. Now, again, remember we said that's a very, very complicated operation, and getting the crew back depended on being able to do that. Those 2 people would then transfer back into the command module. They would discard the command module in lunar orbit, and then the command module would return to Earth, re-entered, land on parachutes, and be recovered by an aircraft carrier. So we need a computer for this. And what do we need that computer to do? Well, the computer needs to be able to navigate between 1 planet and a planetary body, the moon, needs to continuously be able to update its position and its attitude. And attitude just means the direction it's pointing. Knowing which way you're pointing in space is not easy. It needs to be able to control the spacecraft's engines and thrusters. Now you'll notice that on Gemini, we said the computer couldn't actually fly the spacecraft. People still had to fly it. The computer would just tell them what to do. On Apollo, that was not the case. Things had to happen faster than human reaction could handle. And so the computer had to directly control the engines and the thrusters. It needed to be able to perform calculations in real time, needed to be able to display data in real time. That is, it had to be able to say, here's where you are this instant. And it had to receive remote updates from the ground. So some of the computations were still done on the ground at mission control, and they needed to be able to send those results up to the computer aboard the spacecraft. So the answer to these requirements was the Apollo guidance computer. And you see the computer here, or you see it taken apart here. It was developed by MIT, and it was actually manufactured by Raytheon. About 200 of these were made, and the development cost was about $26 million. That was a boatload of money back in the 60s. So it was a very expensive development process. Here's a photo of the computer with its cover off, and a couple interesting comments about the hardware. So first of all, it had a 15-bit word, which is really unusual, but back then there were not really any standards. We didn't have bits and bytes. Well, we had bits. We didn't have bytes. We didn't have the concept that computers always had 8-bit bytes of storage. It had 36 words of ROM and did I say that right? 36K words of ROM and 2K words of RAM. They referred to the ROM as fixed memory and the RAM as erasable memory. And that's actually a pretty good description. The clock speed was about 40 kilohertz. Actually, it was a little faster than that. It weighed 70 pounds. And every lunar mission had two of these computers. There was one in the command module and one in the lunar module. The memory was kind of interesting. It was a type of memory that had never been used before and has never been used since. It was very expensive to manufacture. It was called core rope memory. And it was kind of like core memory, if you're familiar with that. That's not used much these days either. But the little iron cores were actually woven onto ropes of wire. Very labor intensive to manufacture. And the entire program that was hardwired into the computer had to essentially be woven into these iron cores. And the astronauts referred to this memory as LOL memory. And I am not making this up. LOL stands for little old lady, because those are the people who made this stuff. NASA actually hired people who had a gift for weaving or sewing, and that tended to be older women. And they actually built this rope memory, which had to be weaved by hand, all 36K of it. So let's talk about external storage. How about disk and tape on an Apollo spacecraft? Well, guess what? There wasn't any. The entire software for the mission had to fit in that 36K of read-only memory. So the amazing thing about the computer was that it was integrated into the spacecraft, and it could talk to parts of the spacecraft. So it could get input from the gyroscopes and accelerometers that would tell it where the spacecraft was located and what direction it was pointing. It could talk to the optical instruments, which is what the astronauts used to align the gyroscopes and the accelerometers. It could talk to radar equipment. The lunar module had 2 radars. We're going to talk about them. And it could talk to the keyboard that the astronauts used to communicate with it. Outputs, it could control the main engines and the thrusters. It could put signals on the flight instruments, and it could display data. So let's talk about the software real quick. So the hardware in both the command module and the lunar module was identical, but they had different software. They were similar, but because the 2 spacecraft had different missions, the command module was supposed to navigate to the moon, go into lunar orbit, and then head back to Earth. The lunar module was supposed to land on the moon. So very different purposes. The operating system was the same. A lot of the functionality was the same, but what they actually needed to do was different. The name of the software in the command module was called Colossus, and in the lunar module, it was called Luminary. 1,400 person-years of effort went into this software. And looking through the software is pretty interesting. It's actually available today, and I'll show you where you can get it if you're interested in it. Here's a sample of what the software looked like. And the guys that wrote this, and there were women on the team, so guys and gals that wrote this, really had a sense of humor, and reading the comments is really fun. So this is the piece of software, or the beginning of the piece of software that could light the engines. And so what are you going to call the subroutine that knew how to light engines? Well, you're going to call it burn, baby. And that's what they did. So some of the names they used in the code was really creative. We think of this 1960s as the dark ages of computers, but it wasn't. These guys had to work with limited hardware, but they knew how to program, and they wrote some killer software with what they had. Okay, so why was the Apollo guidance computer, the AGC, interesting? Well, it had to do real-time processing. It had to be able to compute its position, handle the engines, and it had to do that in real time. Whereas most computers during that age, you gave it something to work on, it went off and worked on it, and then later it came back and gave you the results. The Apollo guidance computer couldn't do that. It had to be able to control stuff in real time. And it had to be fail-safe. If the Apollo guidance computer had failed in the lunar module, these guys would have died. So they had to make absolutely certain that this thing could not fail. And in fact, even if the software crashed, this computer could get itself back up and pick up where it left off in under 2 seconds. So how did you talk to this thing? Well, so surely we use something like a mouse, keyboard, and a widescreen display to talk to the computer, right? Well, no. This was the state of the art in talking to computers at the time. And this is what most people use to talk to a computer. They use something like a teletype machine that you see here. We couldn't possibly use something like that in the spacecraft. So in fact, enter a piece of equipment that I think was genius for its time. It was called the Apollo Guidance Computer Display and Keyboard, and it was pronounced DSKY, D-S-K-Y, for display and keyboard. And it's that unit right there. So let's take a look at where that was in the spacecraft and how it worked. So here's the lunar module. This is the Apollo 11 crew, Neil Armstrong on the left and Buzz Aldrin on the right. And they're at the control panel of the lunar module. And there's the DSKY right there. Now the computer itself is in an equipment bay way behind them, but this is the piece of equipment that they actually interfaced with and that they used to control the computer. Here's a simulator of the command module, and you can see the DSKY right there. And that's how they communicated with it. So let's take a look at what this was and how it worked. So here's the DSKY, and it's broken up into 3 sections. So we have the indicator lights. There's 14 lights there, and they mostly indicate that something is wrong, although there are a couple of lights that aren't necessarily error lights, but we'll talk about them. And then at the bottom, we have the keyboard. And you can see it looks kind of like a traditional keyboard, the calculator keyboard. There's numbers and signs, and there's a clear key to clear the entry if you make a mistake, and a reset key. But there's some really curious keys over on the left, verb and noun. What's that all about? We're going to talk about that. We've got an enter key, which is used after you've entered a value. You press enter to get the computer to accept the value. And we've got a key labeled pro. That's a commonly used key here. Stands for proceed. And after you've finished entering data and you're ready for the computer to go on with whatever it's doing, you hit proceed. So let's look at some of the parts of the display. The first part of the display is the first, the first number there is the program. And in this case, 63. So the computer had a few dozen different programs built into it. The command module had 44 different programs. The lunar module had 35 different programs. They weren't numbered sequentially, though. That's how you wind up with a number like 63. But they all had 2-digit numbers associated with them. And the crew could run any of those programs that they wanted. So just to give you some examples for the command module, program 11 was the program that ran during launch and monitored the status of the launch. Program 23 was what the crew used if they needed to do a mid-course correction on the way to the moon or on the way home. Program 64 was what they used during re-entry into the Earth's atmosphere. It's what knew how to steer the command module in the atmosphere, and it did actually steer the command module during re-entry. So again, 44 programs in the command module, 35 programs in the lunar module. The next display is verb and noun. And those displays match up those 2 keys that we've got down on the keyboard. I'm going to explain those more in just a second. And then we have the 3 registers. Those are 5-digit displays where the computer can display information and where the crew can enter information. And I'll show you how that works in just a second. So let's talk about the nouns and verbs. They came up with a brilliant scheme for how the crew was going to communicate with the computer. They were going to do it in a very English-like way. Anytime the crew needed to tell the computer that they needed it to do something, they used a 2-digit verb and a 2-digit noun. And this worked just like English. The verbs were commands telling the computer to do something, and the nouns were the piece of data that you wanted it to do it with. So there were about 90 different collections of data that the nouns represented. So just some examples. For example, verb 34 told the computer to cancel what it was doing, and verb 6 told it to display something. So the nouns, each noun represented a piece of data or some small collection of data. So for example, noun 36 represented the mission elapsed time. They started a timer at launch, and noun 36 represented how many hours, minutes, and seconds it had been since launch. Noun 47 represented the weights of the spacecraft. Actually, their mass, but we say weights. And then some of the nouns were collections of data that were useful at the same time. So during reentry, for example, the crew would display noun 64. And remember, we had 3 different displays on the computer. And so noun 64 in the first display would display the G-forces that the crew was experiencing. It would display the velocity of the spacecraft, and it would display the range in nautical miles until splashdown. So the crew had to know 40 to 50 different program numbers. They had to know about 80 different verbs, and they had to know 90 different nouns. How in the world could they remember all of those? Well, there were cheat sheets everywhere in the spacecraft. Actually engraved on the control panels in different places were lists of the common verbs and nouns that they might need. And they'd been training for so long that the common ones they had memorized. Also, if you look in the flight plan, which was the checklists that they were following, what you see is that all throughout the flight plan were instructions on using the computer, and it would tell them which programs they needed to run and which verbs they needed to use and what those verbs and programs did. So they had a lot of help remembering these numbers. And the astronauts always said that they actually found it a very easy way to communicate with the computer. So I want to show you a couple quick examples of communicating with the computer. So we're going to do a couple of different things, and I'm going to pull up a little demonstration I've got a little emulator of the Apollo guidance computer right here. And I'm going to hit reset to turn that light out. Okay. So the first thing I'm going to show you is a lamp test. And I wanted to find some real simple things that were easily understandable. So the lights, those 14 indicator lights on the left-hand side, actually had incandescent bulbs in them. And as we know, those can burn out. So they needed to make sure that when they were about to do something, none of those lights were burnt out. Also, the displays on the right used electroluminescent displays, and they could also burn out. So if you had one segment burnt out, an 8 might look like a 0. It was really important that you knew that all your lights were working. So there's a verb for that. Verb 35 is lamp test. So what the crew would do before a major maneuver to make sure all the lights were working, they'd press verb and then 35, and that gets, oops, sorry, I did that wrong. If you make a mistake, you just hit verb again and enter the correct value. Okay, and so that's the one I want to execute, and I just hit enter. And there we go. I can make sure that all the lights on my computer display are working. Okay, let's try one more thing, or try the next thing. I want to display the mission elapsed time. Now that's noun 46 is the mission elapsed time, and verb 6 allows me to display a value. So what I'm going to key is verb 06. So that's what I want it to do, display a value. And then what I want it to display is the mission elapsed time. That's noun 36. So noun 36 and enter. And we are 12 hours, 39 minutes, and 9 seconds into the mission. Okay, let me show you another one. Suppose I want to display the weights of the 2 spacecraft. So I want to use the 06 verb again. I want to display some data, but the noun is going to be different. The weights of the spacecraft are in noun 47. Now, because I'm going to do the same verb, display data, I don't have to enter that again. So I can just hit noun 47 and enter, and it displays the weights of the 2 spacecraft. So my lunar module weighs 33,500 pounds, and the command module weighs 32,390 pounds. Now, those are just estimates. There's no actual way to weigh the spacecraft in space. So what happened was mission control would keep track of how much propellant got used, how much water got vented overboard, and they would keep careful track of that. And then occasionally they would tell the astronauts, we're estimating your weight right now to be whatever. So the crew occasionally would have to enter that. So how do I change these values? Well, that's verb 24. And again, I would key not noun 47, but since that's already in the display, I don't need to do it again. And I hit enter, and the first line blanks out, and I can use my keyboard to enter. Let's say they now tell me that the lunar module is down to 32,000 pounds, plus 32000, enter. And the command module is now down to 29,800 pounds, plus 29,800, enter. And that's how they changed information. Okay, I'll show you one other thing. One of the things that was interesting about the verbs and the nouns is that the computer could use them to communicate with the crew as well. So it wasn't just the crew telling the computer what to do, it could be the computer telling the crew what to do. So suppose I want to put the computer in sleep mode, what we today would call sleep mode. They called it standby mode. I have a program for that, and it's program 06. So to run a program, I type verb 37. Verb 37 means run a program. And then which program? 06. And now the computer flashes a verb 50 and a noun 25. If I look in my reference, I'll find that verb 50 means please perform. So the computer is asking me to do something. Noun 25 means checklist. So the computer wants me to perform an item off my checklist, and it wants me to perform procedure number 62, which is what's in that display below. So that would tell me to go flip some switches off, and when I've done all of that, I hit proceed, and the computer goes to sleep, and the only sign that it's still getting power is that it's flashing the standby light. So that's an example of the computer telling me to do something.
Excuse me, Mark.
Yes.
You have 8 minutes left, sir.
Okay. I'm going to book along here. All right. So that's my demo. And thanks for that, by the way. So I just want to go over real quickly 3 programs that I think are really interesting. How did they use the computer to land on the moon? So there were 3 programs that ran in succession when they landed on the moon. Program 63, 64, and 66. And let me just tell you real briefly what each one of those did. And I'm going to skip a couple slides here. Okay, program 63 was the first program that ran. They ran that when they were ready to start their descent to the moon. At that point, they were at about 50,000 feet altitude. They were about 240 miles from the landing site, traveling at almost 3,800 miles per hour. And in the next 12 minutes, they would get rid of that 50,000 feet of altitude. They would drop that speed to 0, and they would get down to the surface. So at this point, the computer is doing all of the flying. And the only thing the crew is doing is just monitoring the computer and making sure that it's doing everything that it needs to do and that they're on the correct trajectory. About 8 minutes later, the computer would go automatically to the next program, program 64. At that point, they're down to about 7,000 feet altitude, traveling almost 500 miles an hour, and they're about 2 miles from the landing site. And what the computer would do at that point is it would turn the lunar module from horizontal to vertical, and the crew would get their first view of the landing site. The computer is still flying the spacecraft, but it can now tell the crew where it's going. One of the numbers that it would display is an angle. You can see it here, 42. It's called the landing point designator. And the commander on his window had degrees marked off on the window. And when the computer displayed a 42, that told the commander that if he looked out his window at 42 degrees, he would be looking at right where the computer was taking the lunar module. When they got down to about 500 feet, the commander would flip a switch, and that would switch the computer to program 66. Program 66 was called manual control, but it wasn't really. The computer's still flying the spacecraft, but now the commander is telling the computer where he wants the lunar module to go. He's looking for a flat spot, and he's guiding the lunar module, guiding the computer to fly the lunar module to that spot. And skip a little bit here. All right, so a few pioneering things about the Apollo guidance computer. Logic was built entirely with integrated circuits. As far as I know, it was the first computer to ever do that. It had the concept of priority multitasking. This was new too. Computers previous to the Apollo guidance computer gave everything they were working on equal priority. The designers of the Apollo guidance computer knew that some things were more important than others, and it allowed the computer to work on the most important things first. Digital fly-by-wire, the idea that the crew didn't fly the spacecraft directly, but rather the computer did, and the crew told the computer what they wanted it to do. This is common today. Every Airbus airliner today does this, but back then it was brand new. The idea that you could use a digital computer as an autopilot was brand new. And the entire discipline of software engineering was built as part of this program. And I want to talk real quickly about one of the people that worked on the Apollo guidance computer, Margaret Hamilton. You might have heard of her. She was in the news a few years ago. She was the director of MIT's instrumentation lab where the Apollo guidance computer was designed. She led the team of programmers, as many as 350 people, that designed the software. And in 2016, she got the Presidential Medal of Freedom for her work on the Apollo guidance computer. And that's the highest honor the US can bestow upon a civilian. Okay, I'm going to skip a couple other things. Real quickly, talk about the Apollo guidance computer in popular culture. In 1995, perhaps you saw the movie Apollo 13, one of my favorite movies of all time. Very technically accurate, and the computer appears many times in that movie. And here's a screenshot of Kevin Bacon using it, and they absolutely used it correctly. So mission control has just told him to perform a maneuver. How does he do that? He keys into the computer the information he needs to perform the maneuver. In 2017, there was a movie called Valerian and the City of a Thousand Planets. It was panned by critics, but I really liked it. It was really cheesy, and there were plenty of times when you were tempted to say, oh, come on, really? But I really enjoyed the movie. I thought it was great. At the end of the movie, our two heroes escape in a small spacecraft. And here's a screenshot of that spacecraft. And right there on the control panel is the Apollo guidance computer. Amazing. So, and the last thing I'll mention is that a lot of people, including me, have been captivated by the Apollo guidance computer for the pioneering piece of hardware that it was. And now that we have 3D printing and we have small computers like Arduinos and Raspberry Pis, a lot of people have built replicas, working replicas of the Apollo guidance computer. And I just find that fascinating. So if you're interested in reading more, there are two great books on it, The Apollo Guidance Computer by Frank O'Brien and Digital Apollo by David Mindell. If you want to look at the program behind the Apollo guidance computer, the entire software is available online at that web address, and you can get these slides. They'll send you these slides, so you can get the address there. There is a website called Virtual AGC, and the link is there. And they have a working piece of software that emulates the entire computer, and it actually runs the original software. And they have an enormous library of documentation on the Apollo guidance computer dating from the 60s and 70s. You can actually find the programmer's guide there. And the last thing I'll mention is there's a web series that I really liked. It's by a guy called Curious Mark, and it's on YouTube. And they got their hands on a real Apollo guidance computer. There were no working Apollo guidance computers still in existence. They got one. It was badly broken, and they fixed it. And they now have it running. And they've donated it to somebody. I've forgotten what eventually happened to it. So there is now today one Apollo guidance computer that actually works. So that's it. Thanks for letting me talk about my favorite topic. And I don't know if we've got time for any questions, but if not, you can email them to me.
Yeah, Mark, fantastic. I enjoyed that presentation. It takes me back into the history of what computers were doing. One of the questions that we got was the DSKY software, DSKY software. Is it available online?
Yeah, so it's in, so the DSKY itself did not have any software. The DSKY was just a dumb piece of equipment that connected to the computer, and the computer was off in one of the equipment bays. If you go to that middle bullet point where it says AGC source code, it's in assembly language, but all the software for the computer, including, this is interesting, the name of the routine within the software that ran the DSKY was called pinball. I told you they picked some really good names for some of this stuff. So if you just search for pinball within the source code, that's the code that ran the DSKY.
Pinball, aye. Okay, another question was, how much did the astronauts know about computer systems?
Actually, so they were not computer experts, but they understood this stuff at a deep level. And there were times during missions when they had to key in numbers in octal, and they had to know about internal memory addresses, and they understood that stuff. So when somebody said, I need you to put this octal number in this memory address in the computer, they knew how to do that. So, you know, they probably not of the level of some of the people on this call, but they certainly understood this computer to a pretty deep level.
Fantastic. One other question was, did any companies other than IBM work on the computer systems?
Yeah, so IBM built the computer that steered the Apollo rocket, but the Apollo guidance computer that we talked, oh, and they built the Gemini computer, we talked about that. But the Apollo guidance computer was developed by MIT, and IBM had nothing to do with it. In fact, IBM had a competitor system and lost to MIT.